Hello, I'm Kate. In this video we're going to be working on units, how you use them and their conversions. Unit conversions are really crucial. NASA lost the $125 million Mars Climate Orbiter spacecraft after a 286-day journey to Mars, all because of unit conversion errors. You need to be able to convert your units correctly, as well as working out what units your answers should be in if you're using equations. Let's take a quick look at some common units. As you can see here, for many of these quantities, you have multiple different units that you might need to convert between. So if we look at masses, you might have units in milligrams, or grams, or kilograms. If you look at volumes, you could have mils, centimetres cubed, decimeters cubed, meters cubed. You will often be given a mix of data. You've got to know how to make those conversions between those different units with confidence so that you can get on with the rest of the question without worrying about it. We're going to work on that today. First up, conversion factors. These are conversion factors that you are going to need to be familiar with. We have mega, kilo, deci, centi, milli, micro and nano. Some of them make your numbers bigger, some of them make your numbers smaller. It's worth bearing in mind that a lot of them are powers of 3, so kilo is 1 times 10 to the 3, mega 1 times 10 to the 6, milli 1 times 10 to the minus 3, micro 1 times 10 to the minus 6, and nano 1 times 10 to the minus 9. When you're converting units, always take a moment to think about whether the magnitude of your data is going in the right direction. So if you're going from a smaller unit to a larger unit, then your number should be getting smaller. Let's say you have 5 grams. We want to convert that to kilograms. Well, you're going to do 5 divided by 1,000, which will give you 0.005 kilograms. Your decimal place has gone 1, 2, 3 places to the left. This has got smaller. Whereas if you're going from a large unit to a smaller unit, then your number should be getting bigger. So let's say we have 7 kilos and we want to convert that to grams. Well, what we're going to do is 7 times 1,000, giving you 7,000 grams. Your number has got bigger. It's always worth taking a moment at the end of a conversion just to do that check. It's very easy to end up going in the wrong direction. Your first challenge for today then, and this should be relatively straightforward before we get on to some more complex examples, check that you can convert these values below into your required units. Do take that moment to think, have you gone in the right direction? Pause now. So these are your answers. Let's take a minute to work through how you should have got those, thinking about whether we're getting smaller or larger. So 105 grams to kilograms, that is a larger unit, so we should be getting smaller. So we divide by 1,000, giving you that answer. Meters to millimeters. Milli, again, is a power of 3, okay? But this time we are going to a smaller unit, so our number should be getting bigger. So we do 2.5 times 1,000. Kilojoules to joules, units of energy. The kilo tells us it's 1,000 conversion factor, so 200 times 1,000. When you add your zeros together, you have 5 zeros, making it 2 times 10 to the 5 in standard form. Pascals, units of pressure. Doesn't matter if you know that though, because your clue is in the kilo part, the kilopascals. So we are going to a bigger unit, so we need to be getting smaller. So 300 divided by 1,000 gives you 0.3 kilopascals as your answer. Well done if you got those right. If not, don't worry, there will be more examples in your consolidation exercises for you to practice. Right, if you did do okay on those, here's a chance to challenge yourself. We have some slightly more interesting unit conversions here. Pause now and have a go. Let's have a look at the answers. Here you go, in the correct units. So let's take a minute to work through how we got those. So 25 milligrams to grams. Milli is 1,000. So I am dividing by 1,000 here. I'm getting smaller. So 25 divided by 1,000 gives me 0.025 grams. Right, going from grams to micrograms. Microgram is a smaller unit, so my numbers will be getting bigger. Micro is 10 to the minus 6. So I am doing 200 times 10 to the power 6, okay, because my numbers are going to be getting larger. When I add on those extra zeros in standard form, that gives me 2 times 10 to the 8 micrograms. Nanometers to meters. Nano is 10 to the minus 9, so I'm going to a bigger unit here, so my number will be getting smaller. So 150 times 10 to the minus 9. In standard form, you move that decimal place 2, giving you 1.5 times 10 to the minus 7 meters. Megapascals to pascals. I'm going from a larger unit to a smaller unit. It's a power of 10 to the 6. So 10 times 10 to the power 6. When I move that decimal place to convert it into standard form, that gives me 1 times 10 to the 7 pascals. Well done if you got those right. If not, as you know, the consolidation exercises will help you get a bit more confident. This is where it gets more interesting again, stepping it up another notch, I'm afraid. If you have squared or cubed units, you need to do your conversions slightly differently. And you're basically doing the same thing with the conversion factor. So if we're looking at areas, you've got squared units. If you're looking at volumes, you've got cubed units. And there are, of course, more complex examples that you may come across. So let's look at this example. I'm trying to convert 20 centimetres cubed to metres cubed. Well, to go from a centimetre to a metre, I divide by 100. But I have got centimetres squared, so I need to divide by the conversion factor squared. So I'm doing 20 divided by 100 squared. When I do that, that gives me an answer of 2 times 10 to the minus 3 metres squared. Okay, over to you. Look carefully each time at whether you need to cube or square your conversion factors. Pause now. Let's take a look at the answers. These are the answers that you should have got. I'm just going to take a moment to work through those for you. So here we have centimetres cubed going to metres cubed. So we are getting smaller. It's a factor of 100, but it's cubed. So I'm doing 150 divided by 100 cubed, giving me that answer. Metres cubed to centimetres cubed, I'm getting bigger now. So I'm doing 20 times 100 cubed, which gives me 2 times 10 to the 7. Metres squared to centimetres squared, I'm getting bigger, so I am timesing by the 100 conversion factor, and I need to square that, so 35 times 100 squared, giving me 3.5 times 10 to the 5. Decimeters cubed is probably the ultimate challenge so far. Deci is a tenth of a metre. So when I go from decimeters cubed to meters cubed, I'm getting smaller. So I'm doing 10 divided by the conversion factor of 10 cubed, okay, because it's decimeters cubed to meters cubed, which gives me 0.01 meters cubed. Well done if you got them correct. If not, you can have some more practice. Moving on then to how we deduce our units from equations. We're going to deal with addition and subtraction only first. If you're doing addition and subtraction, you must make sure that your units are the same for the two numbers that you are working with. And in that case, your units will always match those of the units of the values. So let's say we have an initial temperature of 298 Kelvin and a final temperature of 350 Kelvin. To find the temperature change, I'm simply doing 350 minus 298. They're both in Kelvin, so therefore my answer is in Kelvin, 52 Kelvin. If you're doing calculations involving multiplication and division, then you don't do it in quite the same way. What you have to do is take the equation and substitute each of the units in rather than the values to find the final units. If you have units that are on the bottom of the equation, you need to bring them up to the top, inversing the sign. So if they are positive, they become negative when you bring them up, and vice versa. The easiest way to understand that is to have a look at an example. Here we have an example where we have to find the concentration of a solution containing 2 moles of sodium chloride dissolved in 0.25 decimeters cubed of water. Well, the equation for concentration is moles divided by volume. So I put my numbers in, 2.0 divided by 0.25, and I get an answer of 8, which I'm giving to two significant figures like my data. Now I need to find the units. So rather than the values, I put in the units for each. The units of a mole is a mole. The units of volume here are decimeter cubed. So I have mole divided by decimeter cubed. When I bring my units up, I already have mole on the top. This needs to come up to the top, so I inverse it. It was decimeters to the +3. It becomes decimeters to the -3, giving me moles per decimeter cubed. You may sometimes see this written, especially sort of in younger years, as moles per decimeter cubed with a slash. However, it's better to write it in this format simply because it opens the door to you doing more complex conversions. When you're putting together units like this from a calculation involving multiplication or division, you need to know how to order your units. And the rule is that you put positive integers before any units with negative integers. Once you've got positive integers first, then your negatives, you put them in alphabetical order. So alphabetical order within the positive integers, and then alphabetical order within your negative integers. This is the ideal situation. Often though, as long as you have the correct unit, the exact order won't matter too much. So let's have a look at some examples here. Speed, meters per second, positive first, and then the negative. Concentration, positive first, then the negative. Enthalpy, kilojoules first, positive, then per mole, negative. Then on to the most exciting example of the gas constant. We have three sets of units here, joules per Kelvin per mole. Positive comes first, joules. Then we have per Kelvin per mole. These go in alphabetical order. K comes before M, so per Kelvin comes before per mole. Here's an example, which I'm going to get you to do in a minute. We're going to try and find the units for rate. So you are told 50 centimetres cubed of carbon dioxide gas is collected in 45 seconds. You've got an equation, rate is amount of product divided by time. Pause now and have a go at finding that. Your answer should be 1 centimetre cubed per second. Let's check how you should have got that. So the amount of product is 50. The time is 45. When I do that, I'm giving an answer to one significant figure because of the data here being to one sig fig, so that comes out as 1. I then substitute my units in, so centimetres cubed divided by seconds. When I bring the seconds up, it becomes seconds to the -1, giving me 1 centimetre cubed per second. It's really important to make sure that your values always have the same type of units in your calculations. And if they don't, then you're going to need to do a unit conversion. So for instance, you wouldn't do a calculation with one value in grams and another in kilograms. You would need to either convert them both to kilograms or both to grams. Here's an example. It takes Peter 2 minutes to do a lap of the field and a further 25 seconds to throw the balls into the bucket. How long did it take him in total? Give your answer in seconds. Pause now and have a go. Your answer should be 145 seconds. So hopefully this should be relatively instinctive. 2 minutes converted to seconds, we know there's 60 seconds in a minute, so you do 2 times 60, giving you 120 seconds for the lap of the field. It's giving you 145 seconds. So just always remember, make sure that your values have the same types of units. Okay, so that is everything done about units. If you've struggled at all with any of that, and some of that is quite complicated, particularly by the time you're getting onto squared and cubed unit conversions, I highly recommend doing the consolidation exercises. Thanks for working with me today. Bye.